Here's our rover. Here we have the 4 different connections that give power to each of the motors. On the underside of the rover is the battery that powers it. And this is our 5.8 gigahertz wireless video transmitter. And right next to it we have our wireless remote control receiver. The rover is riveted together, and the rover is custom made, as well as its wheels. Here's the camera on the rover, which gives the live video feed to the rover control station, and here's the solenoid lock so the rover can latch into the rover capsule.
Alright, here's our capsule that we made. The capsule is made of sheet steel. We use both rivets and welds to attach it all. The rover goes inside of the capsule, and in the back of it there's an electromagnetic lock, which is controlled by the circuit board. This lock can hold 150 kilograms and will hold the rover in during flight. This will be in the rocket in this orientation and pulled out via the eye hooks with a parachute. And when the rover lands, the board can detect when the capsule has become flat and only release the lock. We showed this in a video. The rover can then drive out and continue its mission. So the lock has wires coming out the back here that connect to this board. We showed the board working in another video where when it sees a flat orientation, the lock unlocks. That's about it. These side rails keep the capsule in place inside the rocket. There are metal rails inside the rocket, so it doesn't jiggle around and mess up the flight trajectory, and it can have a smooth release from the rocket via the parachute. Hello, this is a demo of our remote-controlled rover with wireless video. Our rover is seen down there, and here is our control station. We have a joystick, a control board, a video screen which has the live camera feed from the rover, and a video receiver. So this demo will show the rover's movement capabilities as well as its continued wireless video transmission. So first we'll start with forward movement. The video's been on the whole time. We'll show backward movement now with the live video. See the ground is moving. Prove the rover is showing live video. Next we'll go forward again. And now we will rotate to the left. As you can see, the live video is spinning to the left as the rover is doing her life. Now we can show right rotation. This is the same as left rotation, but other direction. The rover is controlled with skid steer, so instead of using a steering rack, we decided to use steering by moving the wheels in different directions. And the live video has still not cut out. Here's footage of the rover driving on dirt terrain. This demo is going to show the rover locked in the capsule and it being able to leave by itself. The rover is now locked in the capsule. Now we'll set it down, unlock the capsule, and drive the rover out. The rover first needs to drive backwards to reset the lock so it can leave. That's the rover moving backwards. Now we'll drive it forward. And the rover locked the capsule by itself.
So here we have our rover and capsule. The rover is inside of the capsule. I'm going to be demonstrating the landing detection system. So once the rover detects that it is in the horizontal orientation for 5 seconds, it will be able to be pulled out of the capsule. At the moment, it's not coming out of the capsule too much, no matter how much we yank on it. But once we lay it down, we can pull on it, and at the 5-second mark, it comes free.
This video demonstrates when we were testing the range of our video transmission system. My teammate is sitting on the boat pictured in this video, and I have the radio receiving station with the screen where I am. We were able to test up to 0.25 miles of range in this system, and we weren't able to test longer because that's the max distance the lake provided us without losing line of sight, which we are required to have for this video transmission system, which we know. We will show you the Google Maps image where we're able to figure out the distance shown in this video after this. As you just saw, my teammate is on the boat. It's proof of our working transmission system.
To test the video transmission range, we used a boat to travel the length of this lake. We were able to get a video transmission over a range of 0.25 miles, but any further than that, we lost sight of the boat. In real application, we will still have line of sight based on the map of the launch site.
3, 2, 1.
There you go.
This demo will show that the rover can respond to controller input within 5 seconds. Starting with the rover spinning, and I'll switch it between left spin and right spin with a timer on the screen to demonstrate that the movement can be registered within 5 seconds. I'll go right. Left. Right. Left. And right.
This table shows the time it takes the rover to react to input from the joystick. For 5 responses, the reaction time varied from 28 to 36 seconds, or 5.8 to 7.2 seconds per response. The average time per response was 6.34 seconds, with a variance of 0.14.
That was 3 turns in 14.5 seconds.
To find the average time our rover took to turn at 360 degrees, we completed 10 trials where our rover turned 3 times. The average time was 4.751 seconds, with a relatively low variance indicating that our rover is able to turn on a very consistent basis.
This video is proof that a rover can travel 10 feet in 15 seconds. Here's our 10-foot measuring tape, a timer, and our control station. I'll start the timer now. When we hear the motors start moving, that's when our time 0 will be. So right at 8 seconds. When the front tires cross threshold of the measuring tape, we will consider the timer to be done. It just crossed at 20 seconds. So that leaves us with 12 seconds of time to travel 10 feet, which is 3 seconds under our requirement of 15 seconds. This table shows our trials for our test to see how long it takes our rover to travel 10 feet. We set up the rover with the measuring tape as seen in the previous video and turn the rover on to drive 10 feet. This table is our average times and we averaged at 12.963 seconds, which is well under the 15-second minimum that we decided the rover should have for our engineering requirement. We ended up having a variance of 0.3 seconds for these tests.
Our requirements specify that our capsule and rover together weigh less than or equal to 4.31 kilograms. Here we have our capsule fully assembled with our rover inside. Now we will demonstrate that we are underneath the required weight. First we'll zero out the scale. Now place this on. We are at 5.6 pounds. 5.6 pounds is equal to 2.54 kilograms, which is well underneath the 4.31 kilograms that we are required to stay underneath.
Here we have different testing runs of the landing detection system. The landing detection system was programmed to unlock after 5 seconds being in a flat orientation. So here we have 10 testing runs showing an approximate 5-second time. The average time exactly is 5.399 seconds with a variance of 0.057 seconds.